Photoelectron spectroscopy is a technique that can be used to analyze the structure of atoms and gives us information about the electronic structure of atoms. It supports the idea of the shell model, and also gives us information about the ionization energies of particular electrons in a particular atom. So photoelectron spectroscopy is sometimes also abbreviated as PES, and again, what it allows us to do, a definition that you should know, flashcard of, is we use electromagnetic radiation to analyze the electronic structure of atoms and determine their ionization energies. So the way this works is pretty simple. Let's say you have a sample with some atoms on it. We'll just draw one atom to be simple. The idea is we can zap this atom with some electromagnetic radiation. Usually we do this in the form of an X-ray. X-ray. Okay. And we know that since these electrons in that atom are held by the nucleus because of the attractive force, the Coulombic attraction between the negative and positive nucleus, negative electron, positive nucleus, it's going to take a certain amount of energy from that X-ray to eject that electron from the atom. And we know if we have a certain amount of energy that will eject that electron will be released, and it will have a certain amount of kinetic energy, which we can calculate by measuring 1/2 mv squared. We know that the amount of energy is going to depend on which electron we're ejecting, and we also know if we don't add enough energy, that electron won't be ejected because energy is quantized. Think of the photoelectric effect. This is essentially the same thing as the photoelectric effect. So what we're seeing here in this diagram on the right is an energy diagram that represents this process right here. So initially we have two electrons here at the core level, okay, two electrons, and we have some X-ray coming in here that has a certain amount of energy. Well, we know the energy of electromagnetic radiation, we can measure Planck's constant times the frequency, so we can know the total amount of energy coming in. And then, based on what we see at the end, after we zap this atom with energy, we can determine how much energy did it take to kick off that electron. So the way that works is, if we look in the final state here, one of those electrons is now at a higher energy state. And that's because that electron has been ejected. It is now moving with a certain amount of kinetic energy, which the height of this arrow represents. And we know that the total amount of energy that we started with because we know the frequency of the X-ray. So we know that the total amount of energy, Planck's constant times the velocity times the frequency, is going to be equal to the kinetic energy plus some other energy, BE, which we're going to call the binding energy. And that's the height of this line right here. Since energy is conserved, we know the total amount of energy we start with has to be the total amount of energy that we end with. The binding energy, that's essentially how much energy it took to eject the electron from the nucleus. And we know that definition already. That is called the ionization energy. So experimentally, if we know this and we can measure this, we can determine the ionization energy for that electron. So just to give you a visual of what the actual kind of equipment looks like, it's pretty cool. So what we have here is a sample on this kind of gold plate here. Okay, it looks like silicon dioxide, so we're trying to analyze atoms of silicon, Si. We have a focused beam of X-ray here coming in, zap. If we hit those samples of silicon atoms with enough energy, we know electrons will be ejected, boom, towards this analyzer. This analyzer is able to basically determine the kinetic energy of those electrons by figuring out, if we know the angle of curvature of which those electrons come in at, we can use the angular momentum to calculate the velocity, and if we know the mass of the electron, then we can determine the kinetic energy. And then the electron detector kind of analyzes this information, does all the little math, and turns it into a spectrum, which we can get on a computer and print out and analyze very clearly. It's actually a really pretty simple idea, but there's a lot of complexity going on at the same time. So if we do this for various atoms, okay, we can do it for not just one electron, but we can do it for all the electrons that are in the atom. And we can get a spectrum that shows the relative intensities, basically the number of each electrons being ejected, and the amount of energy, the ionization energy, needed to eject each one of those electrons. So if we do that, we get a spectrum that looks something like this. And from this photoelectron spectroscopy, from PES, from this spectrum, we can determine two things. We can determine, number one, what electrons are in what orbitals, and the amount of energy needed to eject them from those orbitals. And we can also determine the element from a spectrum like this. You might be thinking, what? How am I going to do this? There's a lot of numbers. I don't really know what's going on. Well, let's break down what we see. Well, the y-axis is the relative number of electrons. So as you go up on the y-axis, basically that's saying there are more electrons the higher the peak is. On the x-axis, notice it's a little bit inverted. The x-axis is the ionization energy in megajoules per mole. Okay? And notice the numbers get bigger as you go to the left. So what this is showing us, the reason this is kind of practical is it's kind of the way the atom is structured. Think of the nucleus being at where the y and x-axis intersect. Here's the nucleus. So we know as we get further from the nucleus, it becomes easier to rip off an electron. The ionization energy is less as you move further away from the nucleus, which is represented by the numbers getting smaller to the right. Okay? And the closer an electron is to the nucleus, the more energy it takes to rip that electron off, to eject it from the atom. So this just kind of fits with, instead of having the axis switched, this makes more sense for what we know and how we've been talking about the structures of atoms. The numbers at the top of these curves are not these peaks are not the height of the peaks, but they correspond to the x-axis values, basically the exact ionization energies for each one of those electrons. So the way we interpret this, okay, is the height of the peak tells us the number of electrons. Well, let's figure out how many electrons are in this spectrum, how many electrons were ejected from this atom. Well, we know the first orbital, the orbital with the lowest amount of energy, that's the hardest to rip off an electron from, is the orbital that's closest to the nucleus, it's most stable, and that's the 1s orbital. And we know that once we fill up the 1s orbital, then we'll move into higher energy orbitals. Since we see other peaks, here we know that this orbital must be filled. So there must be 2 electrons in this orbital. That is representing the 2 electrons. Each takes 309 megajoules per mole to eject those electrons. So after the 1s2, we know the next lowest energy orbital is the 2s2. And we can determine how many electrons, the 2s orbital, we can determine how many electrons are in that orbital by looking at the height of the peak. Since there were 2 electrons in this peak at that height, and this peak is the same height, there must also be 2 electrons in this orbital. Well, after the s orbital, the next higher energy orbital, that would take less energy to eject electron from, is a 2p orbital. And now notice the peak is much higher. So that's telling us that there are more electrons in this orbital than there were in the s orbital. And we can approximate, it looks like this peak is about 3 times as large as this peak over here. So if that means there's 3 times as many of electrons in this orbital. So this must represent 2p6. After that, we fill up the next highest energy orbital, and that is the 3s. How many electrons? Well, the height of the peak is the same as the other s's, so this must have 2 electrons in it. And then after the 3s, we know comes 3p. Let's compare the height of this peak. Well, that looks pretty similar to the height of that peak. So there must also be 6 electrons in this orbital. So we've identified, each one of these peaks. Now we can determine exactly what element is this. Well, you basically just figured out the electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6. I'm going to leave that to you to decide, to write it out. So therefore, this element must be, it has 18 total electrons, this element must be argon. So So what you need to be able to walk away with today is the conceptual understanding of how photoelectron spectroscopy works. The idea, if we know the energy that's added by an X-ray, we can determine the binding energy or ionization energy because we can measure the kinetic energy of the electron. And you need to know what this spectrum represents, what is on each axis, and how to interpret the data on it.